Hi everyone, I am Dr.S.SURYA, Assistant Professor, Department of Chemistry, A.D.M. College for Women, Autonomous, NAGAPATTINAM. Today we are going to learn about organic photochemistry in MS. What is meant by organic photochemistry? Organic photochemistry is a branch of chemistry that explores the study of chemical reactions and their mechanism initiated by light. Organic photochemistry involves the investigation of chemical reactions that are initiated or influenced by light. Light-induced reactions play a crucial role in the synthesis of various organic compounds and contribute to our understanding of fundamental chemical processes. This field encompasses a wide range of photochemical reactions, including photoisomerization, photodimerization, and photodegradation. The principle of organic photochemistry is based on the photoexcitation and subsequent reaction of excited state species. When a molecule absorbs light energy, it undergoes electronic excitation, leading to the formation of an excited state. The excited state can then participate in various photochemical reactions. Then chromophore and absorption spectra. Chromophore are the specific functional group or molecular entities responsible for absorbing light. Different chromophore exhibit unique absorption spectra determining the wavelength of light they can absorb. Understanding the absorption spectra is crucial for predicting the reactivity of organic compounds under specific light conditions. The type of photochemical reaction: photoisomerization, photodimerization, and photodegradation. We can see one by one. Photoisomerization involves the rearrangement of atoms within a molecule under the influence of light, resulting in isomeric form. Then, photodimerization is formation of dimers by the coupling of two identical or similar molecules upon exposure to light. Then, photodegradation is decomposition of a molecule into smaller fragments due to light-induced reaction. Energy transfer process. Energy transfer mechanisms such as fluorescence and phosphorescence are essential in organic photochemistry. Fluorescence involves the emission of light by a molecule in its excited state, while phosphorescence is a lower or slower emission process with a longer-lived excited state. An application of organic photochemistry. You find applications in various fields, including synthesis of pharmaceutical, photopolymerization, and environmental chemistry. In synthesis of pharmaceutical, light-induced reactions are employed in the synthesis of pharmaceutical compounds. Then polymerization used in the manufacture of polymers and coatings process. Environmental chemistry, studying light-induced reaction helps understand the effect of organic pollutant in the environment. The organic photochemistry is a diverse and important field that provides valuable insight into the behavior of organic compounds under light exposure. It has practical applications in synthesis, material science, and environmental chemistry, contributing significantly to the advancement of the various scientific disciplines. Then basic concept of photons, which are discrete packets of light energy, or absorb the molecule. The energy of the photon must match the energy difference between the ground state and excited state for absorption or occur. The mechanism of photochemical excitation: when absorption of light energy causes an electron to move from the ground state to excited state. The excited state is characterized by high energy and increased reactivity. The electronic transition involves changes in the arrangement of electrons within a molecule. The transition may be from the highest occupied orbital, that means HOMO, to the lowest unoccupied orbital, that means LUMO, or between other energy levels. An excited molecule can undergo various reactions such as photoisomerization, photodissociation, or energy transfer. An application of photochemical excitation reactions have diverse applications, including photophysics, photobiology, and various industrial processes. Example: include photosynthesis in plants, photodynamic therapy in medicine, and photochemical synthesis in organic chemistry. The conclusion of photochemical excitation reaction are fundamental process in photochemistry, enabling the conversion of light energy into chemical changes. Understanding this reaction is essential for advancing our knowledge of various natural and synthetic processes. An experimental technique, the photochemical excitation is often studied using various experimental techniques that provide valuable information about electronic transition, molecular dynamics, and structural changes. The UV visible spectroscopy. The UV visible spectroscopy involves the absorption of ultraviolet or visible light by a sample, leading to electronic excitation. It is useful for determining the absorption spectra, identifying electronic transition, and quantifying the concentration of absorbing species. Then fluorescence spectroscopy measure the emission of light from a sample after excitation with shorter wavelength of light. This technique is sensitive and commonly applied to study molecular dynamics and interaction. The time-resolved spectroscopy tracks the temporal evolution of electronic transition, providing insight into fast process and electronic relaxation. It is valuable for investigating ultra-fast reaction and understanding the dynamic behavior. Then photoelectron spectroscopy measure the kinetic energy of electron ejected from the sample upon photon absorption. The technique provides information about electronic energy level, orbital structure, and chemical composition. Then pump probe spectroscopy used to two laser pulses to steady ultra-fast processes, with the pump pulse exciting the sample and the probe pulse monitoring the changes. It is effective for investigating photochemical reactions and tracking dynamics on short time scales. The electronic transition photochemistry play a crucial role in understanding the behavior of molecules when they absorb light. The definition of electronic transition, they refer to the movement of electrons from one energy level to another within the atom or molecule, typically induced by the absorption or emission of photons. Then absorption of photons, when a molecule absorbs a photon, it gains energy, promoting one or more electrons to higher energy level. The energy of absorbed photon must match the energy difference between the initial and final electronic state. The role of quantum state. The electronic transition involves changes in the quantum state of electrons, including the energy levels and orbital configuration. Then singlet and triplet state. The electronic transition often result in the formation of singlet and triplet state. The singlet state have four electrons in the same orbital, while triplet state have unpaired electrons in the separate orbitals. The Frankenstein principle states that electronic transition occur much faster than the nuclear motion. The initial and final vibration state of the molecule change only after the electronic transition has taken place. Then going to Japan's diagram. The Japan's diagram is a graphical representation of the electronic transition, showing the different electronic state and transition between them. Radiative and non-radiative transition. Radiative transition involves the emission or absorption of photon. Non-radiative transition is referred to involve energy transfer without photon emission, such as vibration, relaxation, or internal conversion. Then application in photochemical reaction. Understanding the electronic transition is crucial for predicting and explaining photochemical reaction. The photoreactivity often depends on the electronic configuration of the molecules involved. Here the Japan's diagram. An explanation to show the Japan's diagram is the transition of electronic state of a molecule during the fluorescence phenomenon. The left axis shows increasing energy, where the typical fluorescent molecule has an absorption spectrum. This spectrum shows the energy or wavelength where the molecule will absorb light. Its convention of fluorescence photon are emitted at a higher wavelength than the photon that are observed. If the incident light is at the wavelength where the molecule will observe the photon, the molecule is then excited from the electronic ground state to a higher excited state. Electrons then go through internal conversion. They are affected by the vibration relaxation and heat loss to the environment. As shown in the figure in the Japanese diagram, the final photoemission transition can either occur through a fast single state, that means fluorescence, or through a slower triplet state, that means phosphorescence. In conventional photoluminescence, photons are emitted at higher wavelength, that means lower energy, than the wavelength of observed photons. Explanation: two non-radiative deactivation processes compared with fluorescence. Internal conversion from the lowest singlet excited to the ground state and intersystem crossing from the excited singlet state to the triplet state. This last process leads to phosphorescence. The Japanese diagram is extremely important to understand for any photoluminescence spectroscopy. When measuring the photoluminescence spectrum, we typically look at the intensity of the emission, its wavelength or energy, and the time over which the emission occurs. The latter is the photoluminescence lifetime. Any number of things can afford this observe, including energy transfer to and from other molecules. Quenching by other molecules, temperature, pH, local polarity, aggregation, or binding. The intersystem crossing is a photophysical process in which an electron transition between electronic state with different spin multiplicity. Typically, it involves the transition from an excited singlet state to an excited triplet state, that means S to T, or vice versa. Here are key points about intersystem crossing. The spin multiplicity, electronic states are characterized by their spin multiples. Singlet state have a spin multiplicity of 1, while triplet state have a spin value of 3. Then intersystem crossing involve the changes in the spin multiples during the electronic transition. The process description: the intersystem crossing usually occurs after the absorption of photon and the promotion of electron from a ground state to excited state. The transition involves the changes in the electron spin, leading to the formation of a state with a different spin multiplicity. The energy conversion: the energy released or absorbed during the intersystem crossing is often associated with vibration relaxation and non-radiative process. The energy difference between the initial and final state is typically released as heat or transferred to other vibrational modes. The role in photophysics: the intersystem crossing plays a crucial role in the overall photophysics of molecules, especially those involved in photochemical reactions. It influences the population of different electronic states and can impact the pathway available for subsequent reactions. Singlet state formation, for example, in the case of singlet to triplet intersystem crossing, the excited electron transition from a higher energy singlet state to a lower energy triplet state. The sensitization and energy transfer: the intersystem crossing is relevant in sensitization process, where the population of triplet state is desirable for certain applications, such as the generation of reactive species in photodynamic therapy. It is also involved in energy transfer process in photosynthetic system and organic light emitting diodes, that means OLEDs. The photophysical application: understanding the intersystem crossing is essential in various scientific and technological applications, including the design of luminescent materials, photocatalysts, and development of optoelectronic devices. In intersystem crossing is a photochemical phenomenon involving the transition of an electron between electronic state with a different spin multiplicity. This process is significant in understanding and manipulate the behavior of molecules in various fields, including chemistry, biology, and material science. The energy transfer refer to the energy transfer of energy from one system to another, and and it plays a crucial role in various scientific and technological processes. Here are key points about energy transfer process. This is defined energy transfer is the conveyance of energy from one entity, example a molecule, particle or system, to another. The mechanism of energy transfer: radiative energy transfer and non-radiative energy transfer. The radiative energy transfer involves the emission and the absorption of photons such as the fluorescence, phosphorescence and photochemical reaction. And non-radiative energy transfer occur without the emission of photon and involve the process like collision energy transfer and internal conversion. The non-radiative energy transfer without the emission of photon and involve the process collision energy. Then collision and vibration relaxation. The collision between molecules or particles can result in the transfer of kinetic energy, leading to vibrational and rotational excitation and relaxation. The vibrational relaxation involves the redistribution of energy among vibrational modes within a molecule. The application in photosynthesis. Energy transfer is a fundamental process in photosynthesis where light absorbing pigment transfer energy to the reaction center, ultimately driving the conversion of light into chemical energy. The efficient transfer of energy between pigment molecule is essential for the overall efficiency of photosynthetic organism. Electronic energy transfer. The energy of an excited electron in one molecule is transferred to the another molecule. This is a common in organic material such as those used in OLED, that means organic light emitting diodes, and other optoelectronic devices. The bioluminescence and chemiluminescence. In bioluminescent and chemiluminescent reactions, energy from a chemical reaction is often transferred to a light emitting molecule, resulting in the emission of light. The understanding and controlling energy transfer process are crucial in the development of efficient energy technologies, including solar cells, light emitting devices, and energy storage systems. In summary, energy transfer process encompasses the various mechanisms through which energy is exchanged between different systems. These processes are fundamental in both natural phenomena such as photosynthesis and technological application, contributing to advancement in field ranging from the biology to material science. Thank you.